Hello everyone. Today we will discuss how to define expectation of random variable in different cases. Of course, you have studied expectation in when you are studying probability distributions, but today we will go with the measure theoretic approach. So, integral with respect to the probability measure. That's how we are going to define expectation. So first, let us define expectation of a simple random variable. So as I said, we are going to define expectation as, in general, integral with respect to the probability measure over entire sample space omega. In the case of simple random variable, what does it equate to? Okay, can we simplify this? So what we know that simple random variable takes only finitely many values, and that is because we partition the entire sample space into finite number of sets. So let me call these A1, A2, A3, A4, A5, A6. Okay, these are 6 sets. A1 to A6, suppose. Then on each of these sets, the random variable takes a constant value, right? So omega is written as union over AIs. In general, we can say I going from 1 to k. Here my k is 6. And we know that x is equal to AI if, so x of omega actually is equal to AI if omega is in capital AI, right? So this integral can actually be written as integral over AI x dp sum over I going from 1 to k. Can I do this? Omega is a union of AIs and AIs are disjoint because AIs are forming partition. So we know that this integral can then be split into k integrals. And now over AI, value of x is just small ai. So this becomes sum over I going from 1 to k integral over AI small ai into dp. Now since small ai is constant, I can take it outside the integral sign. So this becomes sum over I going from 1 to k ai integral dp over ai, and integral of probability measure over a certain set is nothing but probability measure of that set. So this is sum over I going from 1 to k ai into probability of capital AI. Okay. So expectation of a simple random variable is given by this formula. As you can see, it is nothing but the mean of possible values, but not a simple mean. It's a weighted mean with weights being taken from the respective probabilities. Okay. So this is how we define expectation of a simple random variable. It has some interesting properties. Let us list those properties now. So first is linearity. So what is linearity? Linearity says expectation of x plus y or x minus y would be equal to expected x plus or minus expected y. Okay, this is linearity. Then second property says expectation of k times x would become k times expected x if k is a constant. Okay, we have another property. If x is less than or equal to y for every omega in omega, then expected x is less than or equal to expected y. So this is known as monotonicity. By the way, we are talking of only simple random variables. So x and y both are simple random variables. Okay, so as I said, this is linearity. This is monotonicity. Okay. Then okay, so if x is less than or equal to y, then expected x is less than or equal to expected y. That is one property, and extension of that property would be if x is greater than or equal to y almost surely, then expected x is greater than or equal to expected y. Okay, so it doesn't have to be for every omega, it can be almost surely, still it would happen. Okay. This third property, instead of this third property, we can also consider a modified version. If x is greater than or equal to 0 for every omega in omega, then expected x is also greater than or equal to 0. That is, for a random variable which takes only non-negative values, expectation cannot be negative. Let us try to go through the proofs of each of these. So first, let us try to prove linearity. We have already proved that if x and y are simple, then x plus y and x minus y are also simple random variables. That has already been proved. And at that time we saw that x plus y is defined on a partition which is created by ai intersection bj's, if ai's and bj's form partition for x and y. Okay, so let x be defined as sum over I going from 1 to k ai, indicator capital AI, and y be defined as sum over bj, indicator bj, j goes from 1 to say m. Okay, then we know that x plus y, I would prove for x plus y, the proof is almost similar for x minus y. X plus y would be I going from 1 to k, j going from 1 to m, ai plus bj, indicator of ai intersection bj. We have already proved this. Okay. And we also know that this is a simple random variable. So, expectation of x plus y would be sum over I going from 1 to k, sum over j going from 1 to m, ai plus bj into probability of ai intersection bj. Right. This comes from the definition of expectation of a simple random variable which we stated just above this. Okay. So let us try to simplify this. Now, what we have is a finite sum because I goes from 1 to k, j goes from 1 to m. So both these are finite sums. So we can write this as sum over I going from 1 to k, sum over j going from 1 to m, ai into probability of ai intersection bj plus sum over I going from 1 to k, sum over j going from 1 to m, bj into probability of ai intersection bj. We can separate the two terms. Okay. Now since ai is free from j, I can take it outside the first sum. So it would become sum over I going from 1 to k, ai, sum over j going from 1 to m, probability of ai intersection bj plus, since both these are finite sums, I can interchange the order and this can be written as sum over j going from 1 to m, sum over I going from 1 to k, bj, probability of ai intersection bj. Okay. Now, what can I say about this sum? Okay, what can be said about this particular quantity? See, ai is constant and we are taking intersection of each ai with bj. So this sum over probability of ai intersection bj, because each bj is disjoint, ai intersection bj's are also going to be disjoint sets. Right? Each bj is disjoint. ai intersection bj would be subset of bj. So ai intersection bj is also disjoint. And basically, if this is say my all bj's, let us say, suppose these are all bj's and ai is something like this. then we are taking probability of AI intersected with each bj, and when we add those, finally we would get probability of entire AI because they are disjoint. So this is nothing but union over j going from 1 to m, AI intersection bj, and probability of that union, okay, where each of them is disjoint. And because union of bj's is omega, this becomes simply probability of AI. Okay. In fact, this is also known as law of total probability, and we use something like this in Bayes theorem while getting denominator of the Bayes theorem. Okay. So this is sum over AI, and this becomes probability of capital AI. I going from 1 to k, plus sum over j going from 1 to m. Now here again I can take bj outside, so I'll be left with sum over I going from 1 to k probability of AI intersection bj. So by using exactly similar argument, this would become probability of bj, because sum is taken over AIs. So all AIs make entire omega, and this is nothing but what we want. So this is expectation of x, and this is expectation of y. Okay, so we have proved the first property, that expectation of x plus y is expected x plus expected y. You can do similar thing for minus. The second thing is very easy, so I am leaving it as homework. Expectation of kx equal to k expected x. There is nothing, you have to just substitute in the formula. Now let us try to prove this. If if x is greater than or equal to 0 always, then expectation of x is greater than or equal to 0. Okay. So if x is greater than or equal to 0, what does it mean? It means that AIs are greater than or equal to 0 for every I. Am I right? Further, we also know that probability can never be negative. So probability of AI is always greater than or equal to 0. Therefore, AI into probability of AI is greater than or equal to 0 for every I, and therefore sum over AI probability of AI is also greater than or equal to 0, and this is nothing but expectation. So expectation x is greater than or equal to 0. Okay. Now as a result, what happens is, when you have x greater than or equal to y, and if x and y are simple, then we can define a new random variable. So suppose we have x greater than or equal to y, and x and y are both simple random variables. Then x minus y we can define as say z would also be a simple random variable. Okay, x minus y, which is equal to z, would also be a simple random variable. And by the property that we proved just now, expectation of z would be greater than or equal to 0. Therefore, expectation of x minus y is greater than or equal to 0, because that is z. And we already know that this is expected x minus expected y. Therefore, we have expectation of x greater than or equal to expectation of y, which is what we wanted to prove. Okay. Now we want to extend this to almost sure case. Almost sure case means if x is greater than or equal to 0 almost surely, then also we want to say that expectation of x would be greater than or equal to 0. Now what is the difference between almost sure and everywhere? So here it means that there exists some omega, there may exist some omega in omega such that x of omega is less than 0, but if you define n as set of all omegas such that x of omega is less than 0, then probability of n is 0. Okay, so these sets are impossible sets. So we would make use of this fact. Okay, so what we know is x is summation ai, probability of ai, I going from 1 to k. Now we know that some of the ai's are 0, but we also know that for those, the set of all omegas for which x omega is less than 0, that has 0 probability. So let me try to draw picture. Okay, suppose this is, here the value is a1, here it is a2, a3, a4, a5, a6, a7, a8. Let us suppose that a4 and a8 are negative. Okay, so these are negative. So this would actually become my n, because n is collection of all those omegas for which x omega is negative, and we know that probability of n is 0. So a4, which is subset of n, would also have probability 0, and a8, which is subset of n, would also have probability 0. Okay, so let me split this into two parts. So sum over I going from 1 to k, ai probability of ai, but instead of sum over I going from, so what we'll do is, this we can split as sum over all those i's such that ai's are greater than or equal to 0, ai probability of ai, plus sum over all those i's such that ai is strictly less than 0, ai probability of ai. Now in this second part, probability of ai's are 0 because they are coming from a set which has probability 0. So this part would have 0 contribution, and on this part ai's are greater than or equal to 0, probabilities are always greater than or equal to 0, so the total is greater than or equal to 0. Okay, hence if x is greater than or equal to 0 almost surely, then expected x is also greater than or equal to 0. As a result, the monotonicity property can also be extended. So that's a homework. If x and y are both simple random variables, so let me write, if x minus y is greater than or equal to 0 almost surely, that is, if x is greater than or equal to y almost surely, then also expected x is greater than or equal to expected y. Proof is not difficult. It is just an extension of what we did in the earlier proof. Okay. So this is all about expectation of a simple random variable. Now we have to define expectation of a non-negative random variable. Okay. So how do we define expectation of a non-negative random variable? So we have discussed a result which says that given any non-negative random variable, there exists a non-decreasing sequence of non-negative simple random variables converging to that random variable. So we would use that result. Okay. So let x be a non-negative random variable defined on omega script AP. Then, so there exists a non-decreasing sequence xn of simple random variables, non-negative simple random variables, such that xn converges to x. Okay. So how would we define expectation of x? So expectation of x would be defined as limit over n going to infinity, expectation of xn. Okay, because we already know now how to define expectation of xn for a simple random variable. Expected x can be defined as limit of this sequence. Now of course you might have started thinking, what is the guarantee that expectation exists? So whatever we proved just now would help us in proving the existence of expectation. So we said that xn's are non-negative, so expectation xn is always greater than or equal to 0. Okay, and we also know that xn's are non-decreasing. So what we know is x1 is less than or equal to x2 is less than or equal to x3, etc., etc. Therefore, from the properties that we proved, expected x1 would be less than or equal to expected x2, less than or equal to expected x3, and so on. So this becomes a monotone increasing sequence of real numbers, and in fact non-negative real numbers. So it can either converge to a finite value if it is bounded above, or it would go to infinity. Okay, but in either case we can say expectation x is that value. So expectation x can be finite or it can be infinite. We are okay with it. It will never oscillate. That is the point here. Okay, the expectation sequence will never oscillate. It's a monotone sequence. So either it would converge to a finite limit or it would go to infinity, and we are okay with both the scenarios. Is it okay? So in this way we define expectation of a non-negative random variable. Now how do we define expectation of general arbitrary random variable? By arbitrary I mean it can take negative as well as positive values or 0 value. Okay, so expectation of an arbitrary random variable. So here we are going to make use of the positive and negative parts that we defined last time. So let x plus be positive part of x. So x plus is x if x is positive, and it is 0 if x is negative or 0. Similarly, x minus is minus of x if x is negative, and it is 0 if x is positive. So x plus and x minus are positive and negative parts of random variable, but notice that individually both of them are non-negative. Okay, so x minus, even if we call it as a negative part, actually the values are positive because of this part. See, x minus is minus sign into x if x is negative. So if x is negative, then negative x multiplied by this minus sign would become positive. Okay, therefore x plus and x minus both are non-negative random variables. Hence, now we know how to define their expectations, because we have already defined expectations of non-negative random variables, and I had given you homework to prove that x is x plus minus x minus. So expected x is defined as expectation of x plus minus expectation of x minus. Okay, this is how it is defined. Now, if both x plus and x minus, expectation of x plus and expectation of x minus are finite, then of course the final expectation is also finite, no doubt about that. However, if this is infinity and this is finite, okay, so if suppose this is finite and this is infinity, then expected x would become plus infinity. If this is finite but this is infinity, then expected x would become minus infinity. Okay, and if both are finite, it's a finite thing, no problem. But if both are infinite, then we say expected x is not defined. Okay, so expected x is defined only if at least one of these two quantities is finite. If both are not infinite, then we say expected x is not defined. Is it okay? Now we are going to introduce one more term, integrable random variable. Okay, integrable random variable. So it won't matter in case of simple random variable, but it would matter in case of others. So we say that a random variable is integrable if its expectation is finite. Okay, we say that a random variable is integrable if its expectation is finite. So this is integrable random variable. In the next lecture, we'll study further properties of expectation. Let me stop here. Thank you.